Welcome to the tutorial on curve fitting, and here we can inspect the behavior or relationship between two variables. For example, in this circuit we have this Thevenin equivalent voltage, Thevenin equivalent resistance, and the load resistance. And we try to tune RL, we try to change the load resistance and see how the power transfer to the load changes. To model this one, we can use PL equals to VL. But since we want to know the behavior of RL, so we have to transfer this function to this function. So after transformation, and since this is only one loop, IL will be just VTH over by RL plus RTH. And in curve fitting, we would like to know whether which variable is constant and which variable is changing, or which variable could describe relationships like RL and PL. Right. This is our PL and this is our IL. But now in IL, we also have RL, which is a variable that we would like to inspect. So we have to further summarize this thing into just PL is equals to VTH over by RL plus RTH squared times RL. And at this point, we know that we could categorize all the variables into two categories. So the first category is the constants. This is the constant. This is constant. And then another category is the changing variables. So RL is changing, PL is changing. And we may also name the constant variables as our parameters. Here we have a function that have two parameters, VTH and RTH. And then maybe three parameters. The third parameter is RL, but RL is the one we would like to know. So we can also write this one as a function of VTH, RTH, and then RL. And from our experiment, suppose we have these information. The first one is the resistance RL of expected, and then this is VL measured in volt, and IL measured in milliamps. We can find the RL, the load resistance, the of experiment, to be just VL over IL. So equals this one divided by this one. We can also find PL. PL is equals to just this times this. But now we will have the unit problem. because this should be in kilo ohms. And then this RL also in kilo ohms, but we may change to ohms by multiplying 1000. Yeah, because by this way we can say that every variables is in their base units. So this one in milliwatt, right? But we would like to have it in watt. So we may divide this by 1000 because IL is in milliamps. So we divide this by 1000. Here. And then we can get two columns like this. The next is the tool that I would like to introduce to you. It's called Desmos. So Desmos is a graphing calculator that we can put in our data. I can copy this, Ctrl V. This is RL, and this is PL. And to type this thing, you may type like P and then underscore L, just like that. And what this tool did was to like scale the screen to our variables. And the next thing is to type in our formula or our function. So PL. Next is this symbol, the tilde, will indicate the optimization or the curve fitting of certain variables. And we have VTH divided by RL plus RTH times RL. Then I think I forgot square. Yes, this looks right for me. Let's zoom in, press this one to zoom into this data. Here we can see that this is our curve that we have fit. I can change the color, maybe blue. Yes. And we can find the maximum point here. This is the maximum point. Or we can do like VTH divided by 2 RTH. Squared times RTH. Because we know that the maximum power transfer happens when RL equals RTH. So this is like, we can get more digits from this one. Here. And if we zoom out the graph, we can see that if we do the experiment, we can get this graph. For example, if we set our resistance to 10k ohms, we get this amount of power. If we set the resistance to 500 ohms, we get this amount of power. And this is the power transfer curve. Alright, And then since we get those things, we can assume that VTH is always constant throughout the experiment, and then RTH is constant throughout the experiment. And for Norton equivalent circuit, we can also transform this thing, Rn equals RTH, and this In, right? This RL. We can transform this portion into like determinants 1. RTH. Right. And this is just source transformation. Right. So this thing is quite simple, just that it says that the voltage source in series with a resistor can be changed into a current source in parallel with a resistor. So in this case, it is just V equals IR. Just VTH equals to I Norton and then R Norton or RTH. We can use this PL function to optimize both Thevenin's and Norton's equivalent circuit, or in the full circuit, we can regard the full circuit as Thevenin's equivalent circuit, and that's why we can do the same curve fitting for all experiments. To recap, this curve fitting can be used to see the behavior or relationship. In this case, we would like to see when RL changes, how PL changes. And we can do source transformation of Norton's equivalent circuit back to the Thevenin's equivalent circuit, and then do all the same optimizations. We have two parameters, VTH and RTH, that we would like to find the answers. And we have another two parameters that we already know the values, which is RL and PL. And from our experiment sheet, we know VL, we know IL. We just want to calculate the actual RL from the experiment and the actual PL from the experiment. And by those two things, we can plug in to Desmos, to a program called Desmos. Just paste the data and then change the variables, do the optimizations, and we get all of our answers, including the graph. You may capture this graph or just the zoom in graph. Both are fine. Just share the graph, export image, and then we have all the curve. And then you may use some software to label the axis, the x-axis and y-axis. And that is all for our tutorial. Good luck.